Okay, this problem says a Formula One race car with a mass of 750 kg is speeding through a course in Monaco and enters a circular turn at 220 kilometers per hour in the counterclockwise direction about the origin of the circle. At another part of the course, the car enters a second circular turn at 180 kilometers per hour, also in the counterclockwise direction. If the radius of the curvature of the first turn is 130 meters and that of the second is 100 meters, compare the angular momentum of the race car in each turn taken about the origin of the circular turn. Okay. So I'm just going to draw this. Okay. So the mass of the car is 750 kgs. Okay. The velocity is for the first circle is 220 kilometers per hour, and here's the conversion. A kilometer is 1,000 meters. 1 hour is 3,600 seconds. So to convert to meters per second, you just divide this number by 3.6. Okay. Anyway, you guys can figure that out. So this is 61.1 meters per second. And the radius of curvature is 130 meters. For the second turn, it's 180 kilometers per hour, which is 50 meters per second. And the radius is 100 meters. Okay, the problem asks you compare the angular momentum of the race car in each turn taken about the origin. So the angular momentum about for a car going in a circular path is, you guys can look up this formula MVR. Okay. So for the first turn, and this is the second turn for L1, well, the mass remains the same, M1, V1, R1. So 750 kg times V1 is 61.1 and R1 is 130 meters. Okay, so those are the units. So L1 is that. Let's calculate L2, MV2, R2. $100 meters. Okay. All right, actually, so what I'll do is I'll put this in the same unit, in the same power. Okay. So looks like on the second turn, the angular momentum is about 10%, that less than 10% of the first one. Okay. Let's let's calculate another thing. What we'll do is we'll calculate the centripetal acceleration on each case. Yep.
For the first one, we both got 5.9 in the power of 6.
That would make more sense. Yep. All right, that makes a lot more sense. All right, so the angular momentum, it went from 6 to about 4, so about 60%. Okay. All right, let's calculate the centripetal acceleration, and I'll tell you in a second why we're doing this, even though the problem doesn't ask you to do that. Centripetal acceleration around the first turn is v squared by r, 61.1 meters per second squared divided by 130 meters. Okay, so 28.7 meters per second squared. So that's a 3G turn. All right. That's right. So that's a 2.5 G turn. All right. So here's why I did that. See, to make this turn, what it is it's the static friction force between the tires and the road. Okay. So the second turn was not an optimal turn because you could have turned faster. Your tires could have handled that. Okay. So this is the kind of stuff, I mean, if you want to optimize it in a training, you would tell the guy, hey, go faster on that second turn.
Oh, wow.
Right. Yeah, so for $10, you can go advise Formula One racing cars, car drivers. Yeah.
Formula One cars are like the design and the shell, so as they accelerate, the effect of gravity is high.
Okay.
It's strong. Like, don't they say like you could theoretically drive one upside down because
You could fly one upside down.
fly one upside down?
Yep. So what our friend is, what's your name? Lee. So what Lee is saying is, so okay, here's an airfoil. So if this thing if this airfoil is moving in this direction, it gets a lift. Okay. Now, you guys remember the static friction force is mu_s times the normal force. So what you do is if you put a fin like this on the car, you get a force in this direction. You're increasing the normal force. The normal force now would be the weight of the car plus this force, the lift force. And so the static friction force is increased and you can make a faster turn. That's the idea. And of course, this lift force depends on the velocity. The faster you go, so the faster you go, it's some constant times v squared. So the faster you go, the greater the lift. I mean, the greater it's pressing down. Yeah. Anyway. All right. Any other questions before we